Welcome back from the break. We will continue with rates of reactions. If we can just go back to our concept map to see where we should go on. We first did the definition of rates of reaction, and then we looked at the factors affecting the rate of reaction. We spoke about the 6 factors that affect the rate of reaction, and for now I would like us to go look at the ways to measure rate, and then with that ways to measure rate experimentally, I will also show some graphs to just sensitize us as to what will follow afterwards. When we look at ways to measure the rate of reaction, firstly, I said to you in the previous session that there are 6 different factors that affect the rate of the reaction. These 6 factors can be altered, and that will then now change the time that the reaction takes place. But when we do this experimentally, there are ways to do it to make sure that we have more or less an accurate experimental setup. With doing it experimentally, we obviously need the right apparatus for us to be able to measure the rate of the reaction. In the first case, I would like us to measure a decrease in the mass, and a decrease in the mass means that the mass is getting less over time. But that is, what mass are we talking about there? We're talking about the reactant's mass, and then we obviously have to do it, the measurement over regular time intervals. An example that I would like us to discuss here is when we take zinc as a solid and mix it with hydrochloric acid in a conical flask to get to see how the mass decreases over time. Now, just before we're going to talk about how the mass decreases over time, it's sometimes important for you to know the names of the apparatus for in case they ask some of these in the exam. Sometimes they can ask us, how will you set up such an experiment for you to measure the decrease in mass? In front of us, we will now have a conical flask where we will have our reactants in. And in this case, we have zinc and hydrochloric acid. And we can see that we will use a ball of cotton there, but the cotton will not be in the way for the escape of the gas. It will still allow the gas to escape. What you also need is a balance so that you can see the mass. And obviously, if you're going to use a timer, you can see for regular intervals what happens to the mass over that intervals. When we measure the decrease in mass over that regular intervals, we can now go back and mathematically use the equation where we say rate is equal to negative change in mass over time, and that negative change in mass over time will actually now be the gradient of our mass over time for this specific reaction. Now, just before we get there, that negative in front where we speak about rate is equal to negative change in mass over delta T. That negative does not mean that the mass is negative. It just means that because the mass is decreasing over time, we know that it's a negative gradient that we will have there. Back to the graph, we will see we obviously have a mass because our reactants will have a mass. And that reactance is there now in that conical flask that we just spoke about. At the beginning, we will see that we have a steeper slope there, and the slope becomes less steep to a point where it is parallel to the time axis. Now, when it is parallel to the time axis, that is the time where your rate is actually 0. But before I get there, let me start at the beginning. We start with some mass. After a time, the mass is less. After a time, the mass is less. Up to a point, like I said, that segment there, the mass will then be staying the same, meaning that the rate of the mass there will be 0. If we look at this, like I said, initially there is a lot of reactant in the vessel, and you have a fast reaction. The reason for a fast reaction is because we have a lot of reactant that can react to, in a fast manner, form our product. As the reaction go on, you will see that the curve becomes less steep to a point where it flattens off, where it actually stopped. Now, what will let the reaction stop? At least one of the reactants are used up. And how will we know that? As I said, if you read it from your graph, you will see on your mass of reactants axis that you have the same mass for that period of time. And as I said, the expression mathematically will be rate is equal to minus mass over delta T. Another way, I would say, the second way to measure is to go and do the same experiment, but this time we don't look at the decrease. We this time allow the gas to be caught up somewhere. So what we can do is we change the experimental setup, and we want to go look at the increase of the volume of the gas for the second one. So what is the gas that we're going to catch up here? It's going to be hydrogen gas, and this hydrogen gas, with the proceeding of the experiment, it should be released, and it will be released into a syringe, and that syringe will then show how it fills up, and we will then read from the syringe the volume of the gas that's there at that specific time. Now, when we do the volume of a gas, we expect of the volume of the gas that we catch up to become more over time while the reaction is going on. But obviously, there will be some time that your volume in the syringe will stay at the same reading. That means one of our reactants is used up. So back to the mathematics, to work out the increase in volume, we can use the rate as delta V over delta T, where this is your volume, and it can be in centimeters cubed over the time. That can be in minutes, seconds, and the rate is then centimeters cubed per second. Then a typical graph will look like this, where we have a steeper gradient, less steep, having parallel to the time axis, showing that the volume remains the same for that period of time, and the rate of the reaction is then the gradient that we're looking at. Right. So again, beginning, fast reaction, slower, stop of the reaction, flat curve, reaction is finished. Right. The very last one, the third one that I want to look at, is the one that we can do as a practical, a formal practical in grade 12, where we measure the color change, how long it will take for the color to change. And we use here sodium thiosulfate and hydrochloric acid in a conical flask on a white tile with a black X at the bottom. We look at from the top, then we can see as soon as the sulfur precipitates, it will go to the bottom. It will make the color of our solution milky to something that we cannot see through anymore. On that time, we take the time and we link the time to concentration. So we will, for instance, use different concentrations of hydrochloric acid when we use it with the sodium thiosulfate. And now I think we're all ready for an ad break. Let's go for it.